Okay, so in this video, we're going to talk about implicit differentiation. And just kind of as a reminder from college algebra, we say that y equals f of x is said to define y explicitly as a function of x. What that means is you have your dependent variable all by itself on one side, and then all of your other independent variables together on the other. Okay, so essentially you're able to solve for y. Okay, not all functions are like that. Not all curves are like that. And so it's going to be important to have another technique to still get that derivative, that slope of the tangent line to those curves. So what I want to do is I'm going to start with this example here. Now, this is a unique example because we're going to work it two different ways. The first way that I'm going to look at it is actually solving it for y and then taking its derivative as normal. So to solve this thing for y, the first thing I would do is move the 1 to the other side. And then I can factor out the y and divide off what I don't want. So I've got this x minus 1 over x plus 1. And so to find its derivative, I'm not going to spend time doing this on the screen. Instead, we know that it's going to end up being 2 over x plus 1 quantity squared if you work it out. Now that's great, but let's suppose, for example, we couldn't solve this thing for y. Let's suppose that we couldn't get it to a point where it was defined explicitly. So now we're going to look at xy plus 1 equals x and take its derivative implicitly. So to do this, I'm going to know that I want a y prime or a dy dx when all is said and done here. Okay, so I'm going to dx both sides of this. I'm going to take the derivative with respect to x to both sides. Now, remember, the with respect to x part is very important. As I come into this first term here, I've got two factors. I've got an x and I've got a y. I've got a product. So this is actually going to be a product rule. So follow me on this. The derivative, this guy here being the first, this guy here being the second. The derivative of the first with respect to x would be 1 times the second plus the derivative of the second back times the first. Well, the derivative of the second, that's the derivative of y with respect to x. So the derivative of y with respect to x would be a dy dx, right? Derivative of y with respect to x. Now back times the first. Now we have plus, once again, derivative of y with respect to x would be another dy dx. Then we would have our plus 0 for our constant equals a 1. The derivative of x with respect to x is going to equal 1. So now, remember, my goal is still to find my dy dx or my y prime. So now I solve this for dy dx. So if I solve this for dy dx, I'll move the y to the other side, and I'll have x dy dx plus dy dx equals 1 minus y. I can factor out the dy dx now, and then I can divide off what I don't need. So, in theory, if we did this correctly, this should equal this, right? Now, they don't really look the same, but that's okay, because notice this still has a y in it where this doesn't. And because in this particular example, we were actually able to solve the function for y, I'm going to take this y and I'm going to plug it back in right there. So as if I plug that back in there, that's going to be a 1 minus and x minus 1 over x plus 1 all over x plus 1. And to clear this up, if I multiply both top and bottom by x plus 1, because of my complex fraction there, you end up with exactly what we ended up with right there. Okay? So the good news is we got the same answer. The better news is we got the same answer doing it two ways. This way is probably the more traditional, but not all functions can be defined explicitly. If they can only be defined implicitly, then this is the technique we would need to use. Now, to be fair, our final answers in most of these derivatives will have both x's and y's in them, right? If we were able to solve them explicitly to get a y, then we would probably just follow this approach all along. This was, again, a very unique instance where we could do both, and I could show you that they both give you the same thing. Okay, so for this example, we're just going to do the same thing, and this is truly an instant where you can't solve explicitly for y. So we're at the mercy of implicit differentiation, and it's likely that we'll have x's and y's both in our final answer, which again is okay. So the first thing that I'm going to do is knowing we're looking for a dy dx, I'm going to ddx both sides of this thing. So on the left side, when I jump in, once again, it's going to be a product where I have a first and I have a second. So derivative of the first with respect to x, that's really important, with respect to x is going to be a 3x squared times the second plus derivative of the second, which in this case the derivative of y with respect to x would be a dy dx back times the first. Okay, so derivative of the first times the second plus the derivative of the second back times the first. So now we'll move over to the right side of the equal sign, and here we're going to have actually a chain rule. The derivative of tangent we know is secant squared, and then our inside would stay the same, back times the derivative of the inside. So for the inside here we'd have a first and we'd have a second as a product rule. So I'm going to need to multiply that by the derivative of the inside. So the derivative of the first with respect to x is 1 times the second plus the derivative of the second. Now, let me come down here real quick. So here's our second, y squared. And if I want the derivative of this with respect to x, this is actually going to be a chain rule. I'm going to need to take the derivative of the outside by multiplying it down, leave the inside the same, and subtract 1. So that would be a 2y subtract 1, and then back times the derivative of the inside with respect to x. So that's going to give us our dy dx. So there's a chain rule there. We're taking the derivative with respect to x, so if we have a y variable, we still have to get inside of it and take its derivative with respect to x. So let me go ahead and erase that and move back up to the top here. All right, so now we're back. Derivative of that y squared, we said that was going to be the 2y dy dx. Okay, so once again, on that right side, derivative of tangent was the secant squared, leave the inside the same. Derivative of the inside, which would have been a product, derivative of the first would be 1 times the second plus the derivative of the second, 2y dy dx, and then back times the first. And I almost made the mistake I mentioned in the last video of forgetting to put that first back in there. So it's always a good idea to kind of run through, once you get something strung out, run through it and out loud just say it, and most of the time you'll catch any mistakes that you made like I did. So now, in most videos I leave them as unsimplified derivatives because it's just a little bit of algebra simplifying it down, and some of it's a little bit subjective. But this certainly is not subjective. We have to get this thing solved for dy dx. It's absolutely a necessary step to give the derivative. So I need to solve for dy dx. The easiest way to do this is actually going to be to take this guy here, distribute it into both of those terms. Then I'm going to get everything with the dy dx on one side, everything without a dy dx on the other, and then I can factor it out and divide off what I don't want. So let me go ahead and start doing that. So this is going to be nothing really different here on the left side. And on that right side, I'm going to distribute. So I'm going to have a y squared secant squared xy squared plus 2xy secant squared xy squared dy dx. Okay, so nothing new on the left, and on the right I distributed, so I've got a y squared secant squared, that stuff, plus I've got my 2xy right there. That's the x, almost forgot a minute ago, tacked it on back there. And then my secant squared gets thrown in, and then my dy dx. Okay, and so from there, what I'll probably do is move maybe this guy over here, and maybe I'll move this guy over here. It doesn't matter which direction you go, but let's say I move them in that direction. So now I'm going to have this x cubed dy dx minus 2xy secant squared xy squared dy dx equals the right side now of y squared secant squared xy squared minus 3 x squared y. So this guy stays the same, and then I took all of this and I subtracted it over to the other side. This guy stays the same, and then I subtracted the 3x squared y to the other side. Now, everything on the left has a dy dx in it, so I can factor that out, leaving me with an x cubed minus 2xy secant squared xy squared. Nothing changes on the right side. And then finally, I'm going to divide this guy off underneath here. And that should give me my dy dx all by itself. All right, kind of an awkward silence there while I wrote. So if you take a look at what we did here, the only real calculus we did was right here. And that was the implicit differentiation. Beyond that, all the way down, that's just algebra. And it's somewhat messy algebra only in the way that it looks. It's going to be the same thing every time. You're going to get everything with a dy dx on the same side, everything without a dy dx on the other. You're going to factor it out, and then you're going to divide off what you didn't want. Okay? And as promised, you're going to have x's and y's in your final answer, which is perfectly reasonable. But for these types of problems, it's absolutely necessary to give your final answer as dy dx equals. We have to solve for that. We can't give this as an unsimplified, if you will, derivative, because it's not a derivative at this point. It's got derivatives in it, but it's not solely its own derivative. So again, they look a little messy, but at the end of the day, they're really not too bad. It's kind of the same thing over and over again.